Part three of the screencast for this week will be some examples of the electric potential. So here's the first example. You have a positive charge and a negative charge. And the electric field lines are shown, and also the contours of the electric potential. So the example has several parts. Calculate the potential at the origin. Calculate the potential at the point 1, 0. So this is the x, y plane. And 1, 0 would be at this point. X equals 1, y equals 0. And then the third part is calculate the potential at the point 0 minus 2. So this is 0 minus 2 would be about here. All right, so here's the solution. We'll call x the position of the test charge, or the position of the point where we're evaluating the potential. We'll call x sub q the position of the source charge. Then we know the electric field at that point x is q over 4 pi epsilon 0, x minus xq over r cubed. That was a result from last week. And the electric potential is minus the gradient, the electric field is minus the gradient of the electric potential. So the electric field is the rate of decrease of electric potential. And it was shown in the part 1 of the screencast. The electric potential at the point x is q over 4 pi epsilon 0 r. Now what's r? R is the distance from the source charge to the test charge. So r here is a distance. It's the distance from the position of the source, that's xq, to the point where I'm calculating a potential. So, let's start with the point 0, 0, 0. Well, there are two contributions. I have to have the superposition of the potential due to the first charge plus the potential due to the second charge. Now, these are equal at opposite charges, so we'll have a factor q over 4 pi epsilon 0. Well, here, q over 4 pi epsilon 0, and then 1 over the distance. So for this part, the point we're considering is the origin. And the distance here is the square root of 2. So I have 1 over the square root of 2. And the distance here is also the square root of 2. So this one has a negative charge, so that's minus 1 over the square root of 2. And so the potential at the origin is 0. So here's the potential at the origin. It's 0. And you can see it lies on the contour that separates positive potential, which is down here nearer the positive charge, from negative potential, which is up here nearer the negative charge. Of course, the electric field is not 0 at that point. The electric field at that point points at a 45-degree angle to the xy plane. it points towards, well, away from the positive charge and towards the negative charge. So don't confuse the value of the electric field with the value of the potential. Now the next point to consider is 1, 0. So that would be this point. X equals 1 and y equals 0. Now the potential is a scalar, so I don't have to worry too much about directions. I just have q over 4 pi epsilon 0 times the distance. So I'll have q over 4 pi epsilon 0 times the distance from the positive charge. Now that distance is the square root of 5. If I look at this little right triangle, this side is 1, this side is 2, so the distance is the square root of 1 squared plus 2 squared, 5. And then the distance from the negative charge is just 1. So the contribution from the negative charge is minus 1 over 1. So that's the answer to the second question. Now, 1 over the square root of 5 is less than 1. Therefore, this number is negative. So the potential at this point is negative. And you see, it's over here closer to the negative charge, therefore has a negative potential. Now, the third example is 0 minus 2. So x is 0, y is minus 2. So we're down here. Well, this time we should expect a positive potential because we're closer to the positive charge. And again, it'll be q over 4 pi epsilon 0 divided by the distance. Now the distance from the positive charge is the square root of 2. So there's 1 over the square root of 2. And then minus the distance from the negative charge is the square root of 10, because this distance is 3 and this distance is 1. So the hypotenuse of this right triangle is the square root of 3 squared plus 1 squared. It's the square root of 10. 1 over the square root of 2 is greater than 1 over the square root of 10, so yes, this time the potential is positive. It's down on this side of the contour with potential 0. Here's example 2. Consider this electric potential function. V of x is p dot x over r cubed, where p is p naught k hat, p vector, and r is the magnitude of x. So I come out here at some point x. Here's the origin. Then this distance is r. And the vector x is just the position vector relative to the origin. And the problem is to calculate the electric field. So this shows, the picture shows the equipotentials in the xz plane. So this direction is z, this direction is x, and we're not worried about the third dimension. Well, we do have to worry about the third dimension because we have to calculate E. And E is a vector. So indeed, it has 3 dimensions. Well, okay, so you have to know that the electric potential is related to the electric field by this relation. E is minus gradient V. In other words, E, the vector, is the negative of the rate of change of the potential. in the 3 dimensions. Or it's the negative rate of decrease of the potential. The electric field is equal to the rate of decrease of the electric potential. Or if I write this out in terms of the 3 components, Ex is minus dV dx, Ey is minus dV dy, Ez is minus dV dz. The rate of decrease of V in the 3 directions. All right, so it's just a matter of calculating derivatives. Vx is written here, but I'm going to calculate the derivatives in Cartesian coordinates. So I'll rewrite this in Cartesian coordinates. P is P0 k hat dot x is z. So the numerator here is P0z, and the denominator is x squared plus y squared plus z squared to the 3/2 power. That's r cubed. So let's look at Ex. I have to differentiate with respect to x. Now the only x dependence is in this 1 over x squared plus other terms to the power 3/2. So I'll get the derivative minus 3/2, this quantity to the minus 5/2, times 2x by the chain rule. So I'll have 3/2 times 2x, that'll be 3x. And it'll be minus 3/2, this quantity to the minus 5/2. So the minus sign will cancel this minus sign. So the answer will be 3p0 xz, I have this extra factor z that I have to carry along, over x squared plus y squared plus z squared to the 5/2. And Ey is similar. This will be a good time for you to pause the video and work out Ey yourself. And check what you get for Ey. By the similarity between x and y, it'll just be the same thing with this x replaced by y. Now Ez is different because I have to differentiate with respect to z. And z appears twice in this function. It appears in the numerator and it appears in the denominator. Now when I differentiate the factor 1 over r cubed, that'll just be like differentiating with respect to x, 1 over r cubed. I'll again get minus 3/2 r to the power 5 times 2z. And the 3/2 times 2 will be 3. So I'll get a term just like this. 3p0z times z. So I'll get a term 3p0z squared. Now when I differentiate with respect to z, I just get p0 over r cubed. And I can combine that with the other term if I write this as r to the power 5 times x squared plus y squared plus z squared. Okay, now I have to take into account the minus sign as well. So I'll get, from differentiating the z in the denominator, I'll get plus 3p0z squared. And from differentiating the z in the numerator, I'll get minus p0 x squared plus y squared plus z squared. So when I combine those, I'll get 3p0 2z squared minus x squared minus y squared. And the denominator, again, I've combined the denominators x squared plus y squared plus z squared to the 5/2. So let's look at the direction of the electric field on the z-axis. So here's the z-axis. Let me use a different color. So here's the z-axis. What if I were considering a point here on the z-axis? Well, on the z-axis, x is 0. So Ex would be 0. Similarly, Ey. And Ez would be 3p0 times 2z squared. X and y are 0, so it'll be positive. So at this point, the electric field will be in that direction. And you see that's the rate of change of the potential, the rate of decrease of the potential. Now let's consider a point on the xy plane. So let's say on the x-axis. So here's the x-axis. Suppose we're considering a point here. Well, then z is equal to 0. Y is equal to 0. So EY will be 0. EX will be 0 because z is equal to 0. And EZ will be negative. It'll be 3p0 times minus x squared over the denominator. So it'll be in the negative. So the electric field will be downward on this side. This was the electric field upward on this side. So in fact, this is the potential function for a dipole field. This will be a dipole field. It'll point upward here, it'll point downward over here. And you could work out any other point. All right. So that's a case where you have to do the gradient of the potential function. Here's a third example. The problem is to calculate the electric potential, V of x, for a long charged cylinder far from the ends. So here I have a long cylinder. Think of it as a wire. Here's a charged wire. It has charge per unit length lambda. And I want to be far away from the ends. I want to figure out the potential, say, at this point. Now, by the cylindrical symmetry of the problem, you can already see the electric field will point radially away from the wire. In other words, the electric field directions will be rho hat in cylindrical coordinates. So by the cylindrical symmetry of the problem, the electric field at an arbitrary point x will be in the rho hat direction, and furthermore, the component of the electric field will be independent of either z or the angle. So using cylindrical symmetry, using cylindrical coordinates, I have coordinates rho, phi, z. But as long as I'm far from the ends, I can just treat this as an infinite line, and there will be no dependence on z. And furthermore, I have cylindrical symmetry here, rotational symmetry around the z-axis, so there'll be no dependence on phi. Well, there will be a dependence on phi in the direction. The direction will be in the direction of rho hat, the direction of increasing distance, perpendicular distance from the wire. And rho here is the perpendicular distance from the wire. Now this is a problem that you can solve using Gauss's law. In fact, we solved this problem last week using Gauss's law. The flux of E through a little Gaussian surface, a little Gaussian cylindrical surface, will be E rho times the area of the surface, 2 pi rho times dz. And that will be equal to lambda dz by the current density lambda. So solve for E rho, it's lambda over 2 pi epsilon 0 rho. Lambda is the charge density, so that's Q over L. Rho is the perpendicular distance from the wire, so that's the square root of x squared plus y squared. Now, what we're asked to calculate is the electric potential. This gives me the electric field. Well, by cylindrical symmetry and the idea that the electric field is the rate of decrease of the potential will only depend on rho. So the gradient of the potential will just be dV d rho. The electric field will be minus dV d rho. And that's 1 over rho. So what's the function whose derivative is 1 over rho? Well, it's log of rho. So evidently, V has to be lambda over 2 pi epsilon 0 log rho. But don't forget there's a minus sign. So lambda has to be minus. So V has to be minus lambda over 2 pi epsilon 0 log of rho. So dV d rho would be minus lambda over 2 pi epsilon 0 rho. The negative of that is E. And also don't forget, I can add a constant. The electric potential is not really determined uniquely until I give a boundary condition. I haven't specified a boundary condition, so let me just say I can add an arbitrary constant here. Which would be determined if I specified the distance that I meant for V equals 0. Now, I can't really let the reference point be rho equals 0 because that's singular. And I also can't let the reference point be rho equals infinity because the log of infinity is singular. So I would have to take for the reference point some distance. Maybe I would say, okay, let's just say V is 0 at 1 meter. That would determine the value of C. All right, so this is another case where we're really using the fact that E vector is minus the gradient of V scalar. And we figured out what is the function whose gradient gives me lambda over 2 pi epsilon 0 rho. But I used Gauss's law to figure out E. Well, here's the fourth example. Again, calculate the electric potential as a function of position for a charged ring. So I have a ring, and let's set up the coordinate system so the ring is in the xy plane, and the axis of the ring is the z-axis. And the problem is to calculate the electric potential for a point on the axis of the ring. So say for this point here, 0, 0, z. So what's V of 0, 0, z? This is an example where there's a continuous charge distribution. And that's in the textbook by Bauer and Westphal on page 724. They work out two examples. A charged line segment. So you have a line segment with some charge Q and length L. A charged disk. So you have a solid disk with charge Q, some area A. They don't work out this example of a ring, but this example is very easy. So again, we know that to calculate the effect of a charge distribution, you use superposition and integration. And that also works for the potential. So the potential at a point x is the integral over the object, so over the object that has the charge, in this case a ring, dq prime over 4 pi epsilon 0 x minus x prime, where x prime is the position of a little bit of charge dq prime that makes up the object. And you integrate over the whole object. Could be a volume integral, could be a surface integral. In this case, it'll be a line integral. dq prime over 4 pi epsilon 0, now I could just say dq prime is some charge density lambda d phi prime. If I integrate around the ring, 1 over the distance from x, that's the blue point here, to the point on the ring, x prime. Now what makes potential easy is that it's a scalar. So actually for this problem, x minus x prime is the same at all points around the ring. No matter where I am in the ring, the distance to the point on the z-axis is the square root of r squared plus z squared. So I just have in the denominator 4 pi epsilon 0 squared of r squared plus z squared. And then in the numerator, integral dq prime. Well, the integral dq prime around the ring is just the total charge of the ring. So here's the answer. It's q over 4 pi epsilon 0 squared of z squared plus r squared. You could use that to calculate the potential of a disk. I would just separate the disk into a large number of rings, and I would integrate over the ring diameter. I know the potential for each ring, and all I have to do now is integrate over the radius of the rings. So I would have this potential times dr to get the radius, to get the potential of a charged disk. This is a formula you'll need to do some of the long kappa problems. So I hope you've been taking notes during this video. And now you should be able to do the problems involving the electric potential on the long kappa assignment.